with us Lauric Ferrat. He's from France. He's in the middle of the country at the moment, countryside, right? And he's an applied mathematician. And his research is focused on machine learning and also statistical tools to build predictive model for autoimmune disease. And so he has, during his career, he has been part of the National School for Statistics and Information Analysis in France. Also, he undertook a PhD and then was a postdoc at the University of Exeter. And now he's working as a research consultant for the University of Exeter and also for the University of Washington in Seattle. So he's with us today. The title of his seminar is The Use of Machine Learning to Improve Prognostic and Diagnostic Accuracy. The title is really, really appealing. So we are really looking forward to see the presentation. Just telling the attendant that if you have a question, you can just type it in the chat or just raise your hand by the end of the talk. So we will listen to Lauric, and by the end of it, he will be happy to be answering your questions. So thanks very much. And thanks, Lauric. So I give it with you.
Thank you very much. Well, thank you again for the invitation. Really excited to talk about my work for the past 4 years, which involved quite a lot of pro-machine learning or pro-statistical model for diagnostic accuracy. I've been working on both over the for past years, and I'm really happy to share what I've been through during this time. So it's a quite different. Can be quite heated questions in the field. Which one is superior? Is it like new machine learning models, which let's say have appeared in the last 20 years, which can often come from the computer science field, where we don't really know how it works, but it works quite well and have led to very impressive results in specific fields? Or should we stick to good old statistical models, which for some of them are 200 years old, for example, logistic regressions, where we know really well the theory behind it, everything has been well proved. And it's quite a big debate between the two fields, and there are two really different points of view between the two fields. From the statistician, it's a new method approach which is coming, and there's deserves debates between the two fields to know if one field can really bring something to the others, and when can it bring something better than the other one. For my colleague who are computer science scientists, they didn't always have this approach. Most of the time they felt like Thanos. They were not very interested by these old statistical models, which were so bad when most of the time, well, given their experiences. And so not everybody is like that, but it's a summary of the impression I had over the past years. And as a statisticians, and I guess like any statisticians who like to make predictive models to change healthcare, it's a question which is quite important. And we all ask ourselves, should I follow the hype? And as a statistician, we often have this role of pushing in a direction or in another for new methodology. And should I push my team to follow the hype? Then a question we ask ourselves is it always better machine learning? Or if not, when is it better? When I should advise a new PhD student, for example, to look at random forest for on a specific data set or not. And most importantly, as a statistician, we like to use tools that we know really well. When should I be happy to use logistic regression? And I'm sure I'm not missing any useful information for the study I'm doing. So I'm definitely not the first who have thought about these problems. On the right, you can find a large number of people who have already started to explore the questions, sometimes comparing directly to logistic regressions, sometimes not. The problem with machine learning is that it's a bit like statistics. It's a very big field, And there are so many methods that you can't understand each of them individually. We all know that just to understand well linear models, not just superficially, it takes a lot of time. There are some studies which show that which has been done with simulations, but the problem I had with simulations is that they don't always reproduce the complexity of real-world data, and all simulations are based on a model which was made to make the simulations, and so it makes it always easier for a specific model to go well with the model for simulating. And finally, there are studies to compare the method on real-world data, but with strong limitations. Not all of them use non-default parameter settings. So I will go into a bit what is a hyperparameter tuning. So it's not pushing the machine learning to its best. And so it makes it a bit biased toward rule or statistical model. And another approach which was often lacking is that the performances were often studying on only one data set and not validated on external data. So obviously it's a topic which came up in the clinical team in Exeter. And in fact, I had a debate with Andre Hattersley, who is the leader of the clinical team. And he was quite adverse against machine learning models. And at the opposite, I was on the other side. I was thinking that machine learning models could make a big improvement to the data set we were using. And he's the kind of person who just like to see things with numbers and not just a theoretical debate. And so with Anita Linham was finishing her PhD, we decided to test different machine learning methods against logistic regressions. And we wanted to be in a setting which happens to a lot of the times, not a clinical setting where we have all the data from the NHS with hundreds of thousands of observations, but something which was much realistic and which happened quite a lot of times, where you have a small number of observations, around the thousands. You are working with medical doctors who already know which variables are important. You don't have hundreds of thousands of variables and you need to find the good ones. No, you already know which one are the good ones. And you have two data sets, you are very happy with them, but life is imperfect and there are two slightly different protocols. Not enough that the study can't be compared, but you are working in a real dirty world, and so you need to deal with that. So we were hoping to find models which would work on both data sets and go beyond the fact that the data sets were slightly different. And we had two data sets where the clinical question is, can we classify who has type 1 diabetes and who has type 2 diabetes? So taking the information of people who entered, who were diagnosed with diabetes and with the age, the BMI, if there are any autoantibody, their cholesterol, if their sex, their total cholesterol, and their triglycerides, could we know if this person has type 1 diabetes or has type 2 diabetes? So YGX comes from Youth Diabetes Oxford. So one study from Exeter, one study from Oxford. So same country, but different. So I will speak a bit about biology, like that. Even if you know already all the math, you will learn something from a medical side. It's that we have cells, and they need energy, and this energy comes from glucose. And the glucose want to enter in our cells, but our cells don't open like that to any bodies. They need the insulin receptors to receive insulin, which will then open the gate for glucose. And for most of, I guess, 27, if we are 30, 27, 28 people, this is what's happening. But for some people, they can be touched with diabetes, and there are two main groups of diabetes, type 1 diabetes and type 2 diabetes, where it doesn't work like that. For people with type 1 diabetes, their pancreas is, after quite long autoimmune reactions, lose their beta cells, and they cannot produce insulins. And so as there is no insulins, the cells cannot open their channel to accept glucose. And that's really problematic for the cells who don't have enough energy. And there is this increase as well, the glucose level in the body. On the other side, the pancreas is still producing insulin, but for sometimes complex reasons, which can be linked to fat, the cells don't recognize insulin. And so when as the insulin is not doesn't enter the insulin receptors, the glucose channel cannot open, and so people don't have energy in their cells. And so it's two disease which a total different pathway, but we have the same effect. People have a high glucose level, and how do we know which one is what? It's quite important to know which one is one, because the two diseases have a very different way to be treated. For people with type 1 diabetes, as their body doesn't produce insulin, they need to inject it themselves in their body, often 3 times a day after each time they eat, and sometimes more. At the opposite, for people with type 2 diabetes, they can be mostly treated with a diet or tablet. So it's a total different way to treat, and it's quite silly to give for someone who has type 2 diabetes some insulin if they don't need it. And if you give regular tablets to someone with type 1 diabetes, they could die. So there is a weight in the two direction. It's much more dangerous to give type 2 diabetes drug to someone with type 1 diabetes, but there are much more people with type 1 diabetes, with type 2 diabetes. So we have clinical questions now, which can be fixed with predictive models. Now, how are we going to compare our predictive models to know which one is the best? So the first step we took was to select different models. Then we select model performance metrics. We compare the models, both with internal validation and external validation dataset. We wanted to see as well if the performance of some models were dropping more than others, which models tend to stay at a similar level, both internally and externally. And finally, we did some as posteriori analysis to know if the model always gave similar answer to predict one observation, or could it differ significantly? So those are the models we took after many discussions. Those are the models we thought were representing most of the most common and famous machine learning models, plus logistic regressions. So we have random forest and gradient boosting machine, which are based on trees. Then we have multivariate adaptive regression spline, which is the form of which belong to the family of spines models. We have the neural networks, which is an introduction, the k-nearest neighbors, where you just The classification method is try to find who are the closest observation and give them the same output. And finally, the support vector machine. For each of those machine learning methods, there are some hyperparameters. So most of the time, people forget to mention them. Those are values which are determined to which are useful to determine the structure of the algorithms and control the learning process. So, for example, for the learning process, we have the gradient descent. You have different rates. Often this rate can be fixed, and if you have a too small learning rate, you might never find the solutions, but it can be the same if you have a too big learning rate. So this needs to be well thought through, and often what happens is that those machine learning methods have so many hyperparameters that it's easier to just use the standard one, which are often not the optimum ones. You have as well hyperparameters which determine the structure of the algorithm. So here we have an example on the right. If you are using splines, for example, you can have 1 knot, 2 knots, 3 knots, 4 knots, and depending of the numbers of knots, you will have a different functions. And here it looks like having 2 knots or 3 knots or 4 knots will give very similar results. 1 knot will have been a mistake. And if you use the standard hyperparameters, you could use one and miss a good performance of your model. So these are so we run our simulation with a package Caret, which I thoroughly recommend, and we used the standard hyperparameters of each of the methods, which was provided by the package. And you can see that some methods, such as gradient boosting machine, have a lot of hyperparameters in the third column, while if you look at the third row with logistic regression, there is no hyperparameters, and it's one of the biggest advantage with the logistic regressions. It's that everything is fixed and you don't have to think about this kind of problems. So I will go quickly through the method we used to the metrics we used. We used the raw curve and AUC to compare the different methods. It's far away to be a perfect metrics, but it's still, I think, one of the best. One is a perfect prediction. At 0.5 is not better than random guess. And AUC is the probability that the model rank a random positive example more highly than a random negative example. So if you have, which can be really useful, but when you have unbalanced data, it doesn't mean anything, even if you have an observation with a very high probability. If there are much more people without case, this person still have a large probability to not be a case. We used as well calibration curves, which is a method to show how the predicted risk given by your model is close to the actual risk you can see in your observations. And that's quite useful to know if you can trust your models, the output beyond discriminations. For example, if you look at the curve which is below, and when the predicted risk is at 30, you can see that the actual risk is in fact at 0.10. So this model is in fact quite bad if you want to use the probability risk, because you are wrong by a threefold, while a perfect model will give you a curve which will follow the dark line. And finally, we use decision curve analysis.
Sorry, hi, Laurie. Sorry. Yeah, this is a seminar where speakers are interrupted. I'm sorry. We should have mentioned. I love interrupting speakers. Sorry, Laurie. Can you go back? So, what is the difference between predicted risk and actual risk? Predicted by what? Predicted by a model? It cannot be predicted by the model itself.
So, if the model tell you that an observation has a 30% chance to be type 1 diabetes, does this person really have 30% chance to have type 1 diabetes? That's what this curve is trying to show. You could have a model which has a very good discriminatory powers, a ROC you see close to 0.99, but it tells that everybody has a risk to develop the disease of 1 and 0.9, while in fact there are some people who have a probability to develop the disease of 0.
Yeah, just carry. It's just actually there is something in the chat.
I can't see the chat.
Yeah, no, that's different. Okay, sorry, I don't really understand that because predicted. What predicted by what, by whom? This is what I understand.
So predicted risk is the prediction by the model using the information we know about their observations.
Okay.
So you put the information you know about the person, their sex, their age, and the model return you a probability.
Okay.
That's predicted risk.
Yeah. Okay. Thank you.
And the actual risk is if you average, for example, 10 people, and the 10 people have 30% chance to have a predicted risk of 30%, you will expect that 3 of them will develop the disease. So if it was the case, you will be on the middle line. It shows that the predicted risk is the same, which is the actual risk. But if only 1 person developed the disease among the 10 people, while the risk was 30% for each of them, it means that your model is wrong by 20% chance.
Okay.
Is it clearer?
Yeah. Thank you. Thanks a lot.
Awesome. The last metrics which has to be added by the reviewers is decision curve analysis, which is a method which aim to weight the relative harms of false positive and false negative results, such that people can take into account the information that the model is providing to them. And if they are more worried about the disease or more worried about the biopsy, they can. There is a computation we can calculate the benefits, and it helps them to take into account if they want to take a special treatment on another one. So what needs to be summarized with the decision curve analysis is that the higher the curve of a model is, the better the model is. So there are different. So now we have different models, and there is a classic way to avoid overfitting, which is doing cross-validation. So what you do is that you train on 80% of the data set, and you test on the last 20%, and you repeat that 5 times, and you take the average, which gives you an average and a more robust way to estimate your the performance of your models. That works most of the times, but there is a tricky problems when you are working with hyperparameters, because you can consider that each combination of hyperparameters lead to different models. So the problem which could happen is that there are so many models that you are trying out that just by chance you find one which gives a near perfect performances. So it's a bit like p-value hunchings, but it's model hunchings. You just find something just by chance, and you can go to natures and claim you have the best model. So there's one way to avoid that, which is to use nested cross-validation for hyperparameters optimizations. And the idea is that now inside you repeat, it's like a cross-validations, but each train fold, you are going to find one set of, for one model, class of model, you are going to find one optimum hyperparameters combinations, which then doing cross-validations, and then you will fit over the whole train with these hyperparameters combinations and test, measure the performance of the test, and you repeat that. So these are the results, and to first my disappointment, and then I thought it was an interesting result, was that in fact all the methods had really similar performances. They all performed really well for internal validations. The average ROC AUC was 0.96, 95. The worst model were the kind nearest neighbors with 0.93, but they are not so far from each other's. And then when we validated on the external dataset, we found out that logistic regressions, maybe by chance, had the best AUC performance. It stayed at 0.95, so it only lost 0.01 in its performance, but other methods were as well quite good, such as neural networks, random forests, support vector machines. So we were just like, okay, that's an interesting result. Well, but do we have maybe the other metrics will show a difference? And in fact, they did not. So on your right, you have the different calibration curves, and you can see that excepted maybe the plot B and the plot F, overall the calibration curves are really good. They follow the theoretical perfect calibrations, which is on the dotted line. And if you look at the calibration plot of the figure C, which is logistic regressions, you see that it's pretty good. There is a bit of overestimations on the top right, because when the model thinks that someone has, he expects that the person has 100% chance to be type 1 diabetes. This person is in fact has only 80% chance to have type 1 diabetes. But it's not really a big problem, because anybody who has a risk to have type 1 diabetes higher than 10% will be quite well followed up, because we don't want to risk to give them a treatment for type 2 diabetes when they have type 1 diabetes. So quite similar result for the decision curve analysis. All the method gave really similar performances in the region which will interest the clinicians, so between 5 to 30 probability threshold. Logistic regression was giving really good performances, like the other methods. The only one which was given a bit lowest performances was the Kinebus algorithms. So, well, okay, all the methods are giving really similar performances. Is it because they give similar outputs? Even if we try to approach the dataset with very different approaches, do we have the same outputs? And the answer is yes, most of the time. So on the top, above the diagonals, you can see the correlations between on the external dataset, the prediction between different models. And you can see that the correlation is around 0.9 or above. And each dot below the diagonal is one observation which was predicted. And for example, if we look at the second row, first column, it's between the GBM gradient bootstrap machine and SVM support vector machine. And you can see that when the prediction of is low for the GBM, it's low most of the time. It's low for the SVM. There are some exceptions, of course, between, for example, SVM and KNN. Sometimes the prediction can be very different. And there are as well, for example, neural networks and logistic regressions are very close to each other. So the models provided very similar results. So that was the conclusion of our articles. It's like logistic regression has similar performances to optimizing machine learning algorithm. And it's just one example, and we can't do that in every possible study in the world. But over the past 3 years, it has been my experience in other data sets with different diseases, some often in the survival predictive model context, with bigger data sets, sometimes with very imbalanced data. Random forest, survival random forest was as good than the Cox model. So I'm still always, when I have a new data set, I always have a quick look at the machine learning methods. But so far, I never had an encounter with a data set where machine learning were making a huge difference. And I'm not the only one who is observing this kind of results. So I stole a tweet from Professor Collins, where he put some different machine learning methods compared to logistic regressions. And it seemed that it's a quite consistent result. And what is common to all of these data sets is that they are quite small data sets. I think that with very big data sets, where we are in the hundreds of thousands observations, machine learning is much more able to capture complex interaction or nonlinear effects, and it could beat logistic regressions. I've seen that repeatedly. But for a very big branch of clinical studies where we don't have 300,000 observations, but only 1,000 or 2,000 observations, logistic regression can really stand out. And there are very useful advantages to the logistic regressions. It's that it's quite simple to explain to medical doctors or the public. There are a lot of theoretical research around it. It's a well understood method. And this is why I always favorite when I have a machine learning method with similar performances. But in the second part of this talk, I'm going to argue that, well, in fact, it's not that important to have a model which is as good as with the best metrics possible. I will argue that we spend too much trying to fit the best model with the perfect fit, and we should focus on other things. There's, I think it's Dr. Box who said that all models are wrong, some are useful, and and he was at the time not talking about predictive models, but more descriptive models, which were trying to reproduce natures. But it's the same for predictive model. We want them to be useful. And I will add that big problems in our work is that often we do beautiful models which could be useful, but it's really difficult to make them used. And I will talk a bit about my experience in this field. Well, how do I get my model useful and used? The first step is to demonstrate that it can make a difference, not just you can predict things well. And the second thing, which is in fact the most difficult, is how do you make your model accessible to all? So I don't know how I am about time. I have 20 minutes remaining. Okay. So this example was made on a data set of 8,000 children who were followed up at birth, and all of them, every 3 months, we had information about them. And the idea was, can we use this information to know if a child is going to have type 1 diabetes in the futures? And what we found was that a lot of those, there were a lot of variables which were helpful to predict type 1 diabetes. But in fact, we could make a model with only 3 variables, and this model will perform really well with a ROC AUC above 0.9 when you want to predict in the next 8 years. This model uses only genetic risk, family history, and autoantibody. And there were slightly better models where we had in country, weight, the number of cities you had in the past, but we decided to go with a model which was as simple as possible, and we focus more how can we use this model to show it can make a difference. Because having a model which predicts if a child is going to have diabetes, it's really not useful on its own, because at the moment we can't do anything for this child. We don't have any drug to give to a child, and we just can tell them you are likely, you have 10% chance to have type 1 diabetes, but we can't do nothing about it. So not really useful in itself. So what we show was that this model could be used to change the way public health and research is done. So what is done at the moment at the top of the screen is that children with a 10% of a highest genetic risk follow up actively until they are age 10. So in green, and that costs a lot of money. But what we can do by being a bit clever is to use the model, and in the second row, and every year we reassess the risk of a child to develop type 1 diabetes before he is 10. And if the risk is low enough, we just can tell the parent, your child has really low chance to develop type 1 diabetes. So we can remove him from the study. And that's great for everybody. The parents are less stressed about it, even if the child were at high risk when he was born, and you save a lot of money. There's second, a bit more complicated approach where you give a more intense follow-up given the risk of the child using the predictive model. And by doing that, if we go, we found that we could reduce by 50% the number of visits needed for screening. And that's really useful because this kind of study are between 50 to 100 millions dollars, so really expensive. And if you can reduce by 2 the cost, you are much more likely to have more studies like that, or you can increase by 2 the number of children you follow. So just using a model can make a huge difference. And this is something that I'm currently helping at Cascade in the University of Washington in Seattle, where we are currently screening children and giving them a follow-up according to their risk. And well, that's one thing. Now, While you have a model, it's great you are doing your research on in your room, like me, but sometimes you want it to be used by other people. And there's two ways to do it. It's quite easy to do a prototype. I will show you two examples. And then there is another road, which is much harder, which is the road to be legally compliant. So the first one is you can use application programming interface with Plumber, for example, if you're using R and Docker, and people who know a bit of IT can access to your model everywhere in the world, even if they don't know R. Another approach is to maybe more useful with medical doctors who don't have time to set up complex servers and use JSON and so on, is you can share your model with RShiny. That many different methods. Well, those are all the approach which works, they are great, but the problem is that now the legislation has changed and any predictive models in UK is considered as a medical class device. And as soon as you enter in these fields, everything gets much more complicated. If you want to follow the law and not have any troubles because somebody used your model and made mistakes and they think you're accountable, it's much more complicated for you to show that you were following the law. And for that, you need to assess which class your predictive model is. Class 1 is lowest risk. Class 3 is that if your model can lead someone to the death, for example, by providing the wrong drug. And I'm currently dealing with this kind of aspect of predictive modeling, and it's quite difficult. Even on the Medicine and Healthcare Product Regulatory Agency from UK, when I use their link, I quite often find this kind of page. So it's a field which is moving really quickly. There's a lot of jargons for a researcher, which is quite difficult when you don't have a degree in law. But I think it's quite important to be aware of that. There are standards to follow, and there are companies who are really able to follow this kind of procedures. The quote we had from our model was we had quote from between 10,000 pounds to 120,000 pounds, just to give an idea. Then after you have made your models, there are different roles. It's not finished. You need to find some people with different roles: clinical safety officer, quality officer, and so on. And each of those people needs to be paid. So when you're having a model is one thing. Having your model used across the world, even if you don't want to get any money from it, it's quite difficult. So in conclusions, machine learning can be a fantastic tool, but it is not always the good one, particularly for a small data set. Instead of finding just the best machine learning models or statistical model, which will have a really slight difference with another models, I think it's better to focus on impact. And if you think you have a good ideas and a model which can really make a difference, I think it's definitely worth it if you want it to be accepted and used around the world. But if you want to make a clinical practical model, it's a difficult and long path, and you need to be ready. I will just acknowledge Dr. Linam, who started with project with me just before the end of her PhD, Professor Oram, Professor Agopian, who are my clinician mentors. And I don't do it all the times, but I want to thank on the top right, Professor Van Kalster and Dr. Wallish, who has been very thorough reviewers for the paper I showed at the beginning. And some of the ideas in the papers are totally theirs, and I think they're just have recognition for that. And if you want to use some of my code to quickly compare machine learning on a new data set, don't hesitate to take my code. Thank you.
Thanks very much, Lauric, for a very, very interesting talk and very complete, because we many times stop at the step that we create the algorithm, and it's very nice to see that you covered as well the part of the implementation that sometimes, no, I want to say always, is the most important part and the most difficult probably. There are many comments in the chat by Henry Musto. I don't know if Henry would like yourself to comment something, or would you like me to go through your comments? I'm happy either way.
Yeah, you can go ahead. My internet's a bit scratchy.
Yes, so I think that well, the first comment was about if you used any penalization of the logistic regression. Although even it was also my question actually, and the papers that you were showing, they were just comparing usual standard logistic regression. But I'm assuming they were not applying any kind of penalization. Is that right?
No, yes, I didn't. We briefly think about it, and we thought most of clinicians don't use only logistic regressions, and they don't go to shrinkage penalty and so on. And so we thought it would be fairer to use the simple logistic regression, because it's this one we wanted to know if it was worse than the other models.
But the conclusions might be different if you use penalization.
I don't think it would be different, because we only had 8 parameters, which are known to be linked to the disease. 2 or 3 variables were a bit less strongly associated with the disease, such as sex, if I remember well. But in the worst case, they capture a bit of noise, but it wouldn't have make a lot of difference. Well, that's my feeling, but I might be wrong.
Okay, thank you. And Henry was also saying, if you have a paper, and well, if you can share in the chat maybe a paper that covers these ideas of making modeling clinically impactful.
Which one? The first bit, or?
I was just thinking that as this has been recorded and it will be shared the NHR website. People can just look at your papers there. And there's then a comment by Professor Daniel Stoll. He was saying that he used your code on GitHub, and that was very easy to use and very useful. So that's good publicity for your code. Thanks, Daniel. And is there any other question or comment that would you like to do, Cedric, maybe?
Yes, hi, thank you, Lauric. That was very good. So the first bit of your presentation, in which you're comparing logistic regressions and machine learning. So this is a single data set on diabetes.
Yes.
In which all the models are trained, and then you've got an external data set on which they are tested. Is that correct?
Exactly, yes.
And in the case of logistic regression, you're fitting it once, and then you're using the setting of the beta parameters to predict values in the new data set. Yeah, okay. No, that's good. I mean, it is very interesting. I know it has been done, and you've referred to several papers which have reached the same conclusions. But I think, to me, it is quite a serious issue. I mean, you seem to be saying, I think in your conclusion, I think you're quite still a bit about the fact that machine learning can be very useful there. But I think ethically, it highlights quite serious problems, because with global warming and all of this, I mean, machine learning methods do require so much more computational power, and often we are ending up having computers running overnight, sometimes over weekends, over days, just to fit certain models. If in the end, according to some criteria, it's not particularly adding so much more value. I mean, it's quite serious. I mean, of course, logistic regression is just going to use linear algebra to find some solutions. So it is very simple. Don't we have? I mean, I think there is an ethical issue there at heart.
So I think you're really right about. I think we should think about it. For small data sets, even big machine learning model run in less than 20-30 seconds. Even when you go through a nested cross validation, it takes 3 or 4 hours at most. So it's the big question is that when you use it for big data sets, does the improvement of machine learning make it worth that you should not use logistic regression anymore, even despite creating more pollution? I don't think there have been any good study on the problems. It has been evoked many times, but yes, it would be great if somebody made a good analysis on it.
Well, I mean, we could talk about this for hours, but I mean, it's difficult to decide ethically. You see, it's interesting there because the issue of computational power, how would you weight it as far as the output is concerned? I mean, you would need to somehow your criteria, for instance, whether you're using the ROC curve or a calibration curve, then you would need to have some sort of loss function that takes into account the computational requirements of a particular model and then weight this accordingly with respect to some sort of global warming scale. I mean, I think it could be done. I think that would be actually quite interesting. I mean, we are here talking about, fitting different models, and the world around us is burning. I mean, quite literally. So I think that those questions are not trivial. I don't think they're trivial. I think your research is good to highlight this. I mean, it is an important issue. I mean, we have sort of computer servers running overnight, testing, trying to find, the best set of parameters.
Sorry, Zeddy, because we just have 5 minutes to go. Really, sorry. I think that we are going to allow. Thanks very much for the comment. That's super interesting, and most of us think exactly the same. But we have another question. Let's see if Samara has some time for ask. Thanks very much, Samara. When you're ready.
Hi. Thank you very much, Lauric, for this presentation. Very, very thought-provoking. I was just thinking, like a few days ago, I finished a study regarding dementia. I've used two data sets, the cross-sectional data sets and longitudinal data sets. I'm comparing the accuracy of different models. One of the models I've used was the logistic regression. And what I have noticed that the logistic regression worked better with cross-sectional data rather than longitudinal data. As well as it worked like with the labels, with the classes of labels. What I found out, the logistic regression negatively get impacted by the number of the classes that you have. So more classes do you have, less accuracy of logistic regression you get. So I assume that, like with this data set, you are just comparing yes or no, so two binary classes, whether 0 or 1. For me, I was comparing like whether 3 classes, or sometimes with the longitudinal data, 5 classes, like whether the person cognitively normal, mild cognitive impairment, or dementia. So for example, for the cross-section, I have 3 classes. Whether the other one, the longitudinal data, I've got 5 classes with different observation or different diagnosis of the disease. So what I found that with them, like I think I've used different machine learning. So it also depend on the number of classes you have per label, the dimensionality of the data, and also whether the type of observation, whether they are cross-sectional or longitudinal. So
I think you're right. I think I agree with you. Logistic regression won't be the best all the time. It's not what I'm pretending at all. It was just in my experience, other models were not better than logistic regressions. But I think it would be wrong to always discard other models than logistic regressions.
Yeah, that's why no free lunch theorem.
Yeah, exactly. Exactly.
Yeah, thank you very much. By the way, I was looking for your that GitHub, what you call it, the website. I couldn't find it. I would really be grateful if you can just send it to us. Yeah,
I'll do it as soon as I finish answering the questions.
Okay, thanks very much for the comment. So Daniel, very last question of the talk.
Yeah,
comment.
Thanks, Lauric. It was a really interesting, nice talk. I assume your variables you choose were theory-driven. Is this perhaps where logistic regression is better than machine learning if you include only variables which are known to be predictive or most likely to be predictive? So there might be if it's more high dimensional or you need to identify predictors, that in this case, machine learning might be better.
Yes, no, and this is where, well, with elastic net methods, logistic regression can defend itself. I think I'm doing a study where random forest and elastic net gave exactly the same results, but it's true that a simple logistic regression could be terrible in this context. But most of the time, I have found that clinicians has already quite good ideas of what's important and what's not important. And I really like to go this route because I kind of put the responsibility on them to know what they are talking about and having past experience, which will reduce the risk of overfitting. But when we are working with genes, for example, we don't have the choice. There are 20,000 genes. Nobody knows exactly what genes are doing. And so you need to use methods to do that.
Thanks.
Okay, thanks so much. Now let me check. There's another comment here. It was Daniel. Okay, so I think that now it's exactly 4 o'clock, so we're gonna leave this for finished. Many thanks, Lauric, for this very nice and lively discussion on your talk. And want to say bye? And today's the last talk for today. Well, Hilton voice actor. Thanks very much, Lauric, and hope to be in touch with you. And thanks everyone for joining. This is we are gonna have a break on our